Now that we've done a significant investigation into chip selects and memory maps and so forth, let's go back and talk about this thing called the memory hierarchy. And remember, the memory hierarchy in general has kind of 4 levels, right? This top level, we had registers. Those were kind of the scratch pad memory inside of the processor. And then we had very close to the processor some high-speed memory called the cache. And then outside of the processor, we had main memory. And for those of you who have been inside of a computer, not literally, but who have gone and investigated the parts and components inside of the computer, you've seen the main memory as those DIMMs, those boards that clip in to the motherboard. And then off of the motherboard, you have long-term storage. And the long-term storage is things like hard drives, tape drives, optical drives, and so forth. Now, what we've really been talking about is kind of the interface that is sitting at the main memory. In other words, all of the different memory resources that are available to you through a flat address space. And in fact, this is kind of, we're going to give you a little introduction here. We've got something called random access memory. And you've probably heard this term before, RAM. Now, RAM does not mean just the volatile memory that we're accessing, to store our variables in the programs that we're running. It's actually the method by which we access elements in memory. And it has a lot to do with the process. So I give a random pattern of 1s and 0s on the address lines, and a memory returns a value back to me. And regardless of what that pattern is, regardless of how far the previous pattern is from the next pattern, it always takes a consistent response time. There's always a consistent response time. Now, the long-term storage, there's actually 2 methods of accessing something, an element from there. And these methods, well, first of all, let's talk about the really slow, the one that's really far away. This one's referred to as sequential addressing. And so there are basically, we've got random access memory. That's one way of addressing. Sequential addressing means that I've got my element that is doing the reading and the writing at a certain position in the stored elements. And if I want something from a different position, I have to sequence through all of those items before I can get to the other one. Think of a tape. So you've got your tape positioned at a certain point in the data. If I want to get to a different point, I have to go through all the tape that is between here and that destination before I can get the data that I'm looking for. That is referred to as sequential. But you also have, so this is really, you're looking at tape. And then we also have something called direct addressing. Now, direct addressing, this is really what you're talking about when you're talking about a good old-fashioned hard disk drive, the ones with the spinning platters. The time it takes to retrieve data depends on where my read-write head is at this moment and where the read-write head needs to be to get the data. But it's a 2-step process. With tape, it was a 1-step process. I'm here, I need to be there, I have to pass through all that data between here and there. But with direct addressing, what happens is I can jump to a block, I can jump to a sector, I can jump to the vicinity where the data is. Now, once I've done that jump, then I do a shorter sequential process. I go through the data in order to get to the data that I'm looking for. So, tapes, sequential addressing, direct addressing, hard drive, random access memory addressing, that's main memory. There's one more, and that's the cache, and that is called associative addressing. Now, associative addressing What that does is it says, okay, there's no real address, there's no real position to expect the data in. What I need to do is take some sort of an address and something that will allow me to identify what address the data came from. So when I'm storing data in a cache, I'm actually storing two pieces. I'm storing the data and I'm storing the address where it came from. And so I'm associating, and it's called a tag, I'm associating a tag in the cache with where it came from in main memory. We'll get a little bit deeper into that when we start talking about caches, but let's take a second and talk about one other issue whenever it comes to the memory hierarchy that we talked about back a couple episodes ago. As you go down through the memory hierarchy, remember there were a couple of things that improved. One of the things that improved was the cost per bit. Okay, so it got cheaper to store a bit as you got farther away from the processor. Remember, the processor is right up here at the tip of this memory hierarchy. The other thing that improved was the overall capacity. But what did we lose? Well, one of the things that we lost was speed. As you go closer to the processor, the access time is quicker. Now, there's a couple of reasons for that. First of all, let's talk about just the general size of the memory itself. If I'm having to go through a lot of data, a lot of memory in order to find the data that I'm looking for, I mean, you can just think it should take longer, right? When we talked in episode 68, about address decoding, we talked about how a NAND gate could be used to identify based on the inputs coming from these address lines, A0, all the way on to N-1. So if I've got these N bits that are identifying an address within a memory device, then these address lines have to go through different NAND gates in order to identify the memory location in main memory that we're trying to access. Well, if I've got N address lines, that means I've got this NAND gate needs to have a certain number of transistors in order to access, in order to recognize what pattern of ones and zeros we're looking at the input. If I make the memory a little bit bigger, this N gets a little larger. This becomes a little bit more complicated, and by making the NAND gate a little bit more complicated, it becomes a little slower. By getting a little bit slower, well, takes longer to find the memory that we're looking for. So that's one of the reasons why as you go down in the memory hierarchy, as you make larger and larger memories, it takes longer to find what we're looking for. Also, another reason why it takes longer to get data that's farther away from the processor is that it is physically farther away from the processor, and it takes time for those signals, a very, very short time, but it takes time for those signals to get back and forth between the processor and the device. So physical space is making it so that speed is a little slower. But there's one other thing. Remember this cost per bit? That cost per bit is saying that the technology that we're using as we get farther away is getting cheaper. Cheaper technology typically means it's slower too. So let's talk about two different types of technologies that distinguish the cache from the main memory. Let's go ahead and make some room on the board. All right, so first, let's talk about the faster of the two technologies. So we have one type of technology that the RAM cache is implemented in, and we have one type of technology that the main memory is implemented in. Let's start with the RAM cache. Now, back in episode 56, we talked about storing data using NAND gates. Now, really what we're doing is we're storing them with transistors. Now, transistors are basically just switches. They're electrically controlled switches. In one type of transistor, if you put a 1 into the input, it closes the switch. In another type of transistor, if you put a 0 into the input, it closes the switch. Let me show you this diagram using both of those transistors. So what I've got is, and I'm going to hopefully be able to explain this diagram after I've drawn it. All right. Now these little schematic elements here, the ones that look like a kind of a little box that's interrupted this line with another parallel line to the inside. I don't know quite how to describe this. This guy right here is what I'm going to use as a transistor. And what we've got is the switch is going to connect A to B if C is a logic 1. This guy right here says that A is connected to B if I turn on or make C equal to a logic 1. So that closes the switch. We also have this type of schematic element that connects A to B if C is equal to a 0. Looking at the little inverter right there, that gives you an idea of exactly how these guys work. So I have 4 of these little transistors in here. Now, the way this works is I put and we're just going to talk about some sort of a positive DC voltage here. Now, that positive DC voltage, that represents a logic 1. And then on this end right here, I'm going to have 0 volts, which is kind of represented with the ground symbol. So, what I've got is a logic 1 here, a logic 0 here. And connected to these, I'm going to create these connections like this. The way this works is that this position right here, this rail right here, this is Q. And this guy right here is Q bar. All right. So if I have a 0 on Q, a 0 on Q is going to close that switch right there, open this switch right here. Closing this switch right here will connect my positive voltage, in other words, my logic 1 to Q bar. Q bar is now a logic 1. The logic 1 coming over here closes this switch, opens this switch, closing this switch connects it to ground or 0 volts, the logic 0. And so by doing this, it's almost like, well, it's a lot like that remember that SR latch that we were using before. We have a 0 here, which closes this switch, which makes Q bar a 1, which closes this switch, which keeps Q a 0. All right, we flip it around. If Q is a 1, Q is a 1 closes this switch, which makes Q bar a 0. Q bar being a 0 closes this switch, which makes Q, or keeps Q, a logic 1. So there's how we store the bit. Now, how do we actually get the bit into this latch? Well, we first make some room, right? What I need to do is connect my Q and Q bar to the outside world, to those data rails, the data lines that we are using to access the data from the processor. So I actually will have a Q and a Q bar that are like that, but I want to leave this cell connected unless the processor is specifically asking to communicate with this cell. So the way you do that is you put 2 more transistors. All right. Now these transistors I'm going to have turn on when there's a logic 1. And remember from episode 68, we talked about this thing called an address decoder. And the address decoder says, well, address decoder. The address decoder, it goes active. And in this case, we'll just say it's a logic 1 when it's active. So the processor has put an address on this address decoder line. It's gone active, turned to a logic 1. It closes these switches, which connects you to the Q and the Q bar. So when the processor wants to store data, it simply puts a 0 and a 1. Like if it wants to store a 0, it'll put a 0 here, a 1 here. That comes through, sets the transistors so that and it has to activate the address decoder line, closing these switches so that 0 and 1 come in and set the transistors appropriately. If the processor wants to read the value, it sets the address decoder line active. That connects the transistors, and whatever this closes these transistors going to Q and Q bar, and that connects the value that's stored inside there to the data lines. Now, that works really well for a number of reasons. Number one, transistors are active devices. So whenever they are turned on, there's actually pressure pushing this data out. Much like if you were to open up the faucet. If you opened up a faucet, the pressure forces that one out. And so quickly the data is output to Q and Q bar. The problem is that it's an expensive technology. And it also, well, it's a little bit larger than the technology that we're going to use to implement the main memory. Let's show you what the circuit looks like for main memory. Now, before I talk about the circuit that is used for main memory, let's talk about a device called a capacitor. Now, anybody who's had experience with electronics is probably familiar with the idea of a capacitor. A capacitor is made up of two plates, two conductive plates that are separated by a dielectric. So what I've got here is I've got a conductive plate separated from another conductive plate, and there's a dielectric in there that makes it so that any charge that is over on the one plate it attracts an opposite charge from the other plate, but yet doesn't allow the two to pass through. So if I put a whole bunch of electrons, if I put a negative charge on this one plate, then the dielectric and the plates being so close together allow positive charges. In the terms of electrical engineering, they're called holes. A positive charge to accumulate on the other plate. And so that diagram right there really is you're capable of storing a 1 or a 0, right? So what I do is if I want to store a 1, I simply put a whole bunch of negative charges on one plate and a whole bunch of and attracting positive charges to the other plate. I've got a logic 1. If I get rid of all those charges and clear them all out, that's a logic 0. So I've stored a logic 1 or a logic 0. How do you actually do this? Well, you once again take the address decoder, and so what you're really looking at is you've stored this value on here, and then you simply connect this to a switch controlled by the address decoder. All right, and if I close that switch, then I can get my data. Really simple. Now, this guy, hey, I've got one transistor. I have 6 over here. I have one transistor over here and a small capacitor. So what you're looking at whenever you're trying to compare these two is this guy is definitely smaller, physically smaller than this guy. This guy is also cheaper per bit. All right. So if you're thinking about that memory hierarchy, as you go down through the memory hierarchy and you want to get a higher capacity, right? Well, high capacity requires that you have a smaller required area to store a bit. So I'm shrinking down the amount of space it takes to store a bit. This guy, the winner, right? Cheaper per bit. There's only 2 small devices here, whereas you have 6 transistors over on this one. So this one is also cheaper. So as you're going down through the memory hierarchy, this guy, that's the way to go. There's a problem though. There's not a lot of pressure coming from this. You know, I talked about if you're looking at transistors, pressure, trying to push that 1 or that 0 out. You're looking at, you know, if you're turning a faucet open and have water pressure that's pushing the water out. Close the faucet, you turn that off. This guy, a little bit more like pouring water out of a cup. There's not a lot of pressure there. The pressure that's there is just supplied by the charge that's on there. And if I am going to use the address decoder to close this transistor, that's going to, when I do a read of this, that's going to take some of those electrons and they're going to flow out through that transistor. Flowing out through that transistor, you're depleting the charge that's on there. So there's not a lot of pressure. We also have a depletion of charge just because every once in a while, one of these electrons is going to escape over to the other side. The dielectric's not perfect. Every once in a while, we get this leakage of one electron just escapes over to the other side. So even if we don't do a read, we've got this depletion that slowly occurs over the course of milliseconds that we're going to lose the charge that's on that thing. So that leakage current and the fact that we've got this drain of current or drain of electrons anytime we read it means that it requires refreshing. What does that mean? That means every once in a while, some sort of a processor that's on the memory device itself has to go through and read all of those values and write them to boost them back up, to give them pressure again, okay? Well, all of that means that this guy is faster. The transistor circuit is faster, all right? Now, memory that's developed out of these capacitors, that is referred to as dynamic RAM, otherwise known as DRAM. All right. This transistor-based technology is referred to as static RAM, otherwise known as SRAM. And like we talked about with the memory hierarchy, they have different applications. This guy right here is typically used for your main memory. This guy right here is typically used for your RAM cache. The more expensive, smaller memory that's closer to the processor usually uses this static SRAM. The processor accessing main memory, it's accessing dynamic RAM. Now, once again, these guys, smaller, cheaper, and slower, means that it's going to be further down in the memory hierarchy. Faster, more expensive, a little bit larger because you can't have the same data density, means this guy is probably going to be closer to the processor. In a later episode, we'll talk a little bit more in depth as to how the processor is interfacing with this DRAM.